Actually, I have a question to previous speaker. Nicola, are you still in this room?
Yes, I'm here.
Yeah, thank you. And I have a question about your the last result of your slides. I think
Yes.
The niobium disilane nanowire device. It's is it also a Josephson junction device from your opinion?
Yes and no, and in the sense that you can see it as a S constriction S device.
Yeah.
So there is no interruption, no N part. So it's not a SNS for sure. We do not see any signature of Fraunhofer pattern. That is what would be your real signature. So I think we can describe this as a. So I see it more as a plain film, so not really as a junction. You can always, I mean, the boundary between plain film and junction is not so clear cut. In the end, a junction is something where you can consider the bank with the fixed phase and all the phase jumps in the region that you call link. But yeah, not an SNS junction. So the order parameter never breaks down.
And also, I think you mentioned the superconducting diode effect in the niobium disilane nanowire device. And do you consider the magnetic chiral anisotropy in your device? Because I think I've read a paper about the non-reciprocal transport measurement in few layer niobium disilane superconductor samples. They measure the second harmonic response of the few layer, but it disappears when they measure in bulk samples. So do you have some the similar result?
I might have escaped this paper actually. Could you send me the link? I might have. I'm not sure also.
I think I can share screen if I'm allowed.
Oh, great! It will be even more live.
Yeah. Can you see my screen?
Yes, I see. Oh, wait. I know the paper, of course. This is still a non-reciprocal resistance. Is what Professor Nagaosa talked about. So this is before the Teruono. So this is still non-reciprocal resistance. This is measured with these 2 omega techniques, and yes, this. But this is not a difference. So it's not fully in the superconducting state. So it's not a difference of critical current. This is the non-reciprocal resistance, which is boosted by superconductivity. Precisely what was discussed today by Professor Nagaosa. This is not the magnet. So this gamma is now called gamma S. So just to go to the history, a non-heterosymmetric metal with Rashba-Spinor interaction with the field shows this non-reciprocal resistance. Normally, this effect is very, very, very small. But if you go in the fluctuation regime close to TC of a superconductor, you can boost it a lot. This is so-called gamma S, because the scale of energy is not anymore the Fermi energy, but is the gap. But if you go at very low temperature, the effect disappears because you need a resistance to start with. This is again non-reciprocal resistance. So I would give him another name to what we measure, because we measure the inductance, the effect of the inductance. And this requires to stay full, so the 0 Kelvin limit, if you want. So far from the DC and absolutely without any resistance. So this is, there is a substantial difference between that. I don't know if I answered your question or if, so what was the question specifically?
I mean, actually, this is also a confusion point for me, because I see in that Superlattice paper, they measured they observed the superconducting diode effect, and they ascribed the superconducting diode effect to the magnetic current anisotropy. So I thought the magnetic carrier anisotropy will definitely result in the superconducting diode effect. But yeah, in this discussion, as it seems my previous understanding is not correct.
Yeah, magnetochiral anisotropy, you have to always specify of what. Any quantity can show a magnetochiral anisotropy. So a dependence in the if you want, on the field and in the current. So this is clear. In this case, is magnetochiral anisotropy for the resistance, and in my case is for the inductance. So in the zero resistance regime. So it's crucial because this paper appeared before the Teruono paper and mine after. So this is the basic difference.
Yeah. Okay. Okay. Thank you.
I might add that a natural question to my work is why people don't measure the kinetic inductance in plain film. It's definitely possible, and I think it will be done. The only thing one has to pay attention that, as was discussed yesterday by Dennis Cohen, as soon as you have vortices, they get pinned somewhere, they have a huge inductance. And in this case, in plain film, they will dominate the effect. You have to be extremely paranoid in compensating the out of plane field. And this is one point. And also you need a device where you can make a long meander, because the inductance is an inductance per square. And you have to get a decent signal need long meander, which is easy to do on wafer, like indium arsenide. A bit more challenging to do this niobium diselenide that you exfoliate and you have a small crystal. Maybe easier for MBE grown niobium diselenide. I don't know. But this is work for the future.
Yeah. Okay. Thank you.
There were a few other questions from before for some of the previous speakers, but I think none of those speakers are here at this point. Although maybe there are some people who can answer some questions. So for example, for Liang, Haifei Kang asked if the F of a low state in the superconductor ferromagnet heterostructure is due to a gauge field or an exchange field. Does anybody in the audience happen to have the answer for that?
Gauge field is a very interesting terminology. You know, there is a lot of mess with gauge field, so-called. What is a gauge field? because gauge is not a field, it's like a mathematical transformation. That's why when people say that superconductivity is a consequence of gauge field, of gauge breaking, that's just not correct.
Yeah.
Just a transformation which doesn't change the physical properties of the material. So I'm not sure what the person means by gauge field, but if this person is confused, as many other people, with this gauge breaking, symmetry breaking, I would suggest to read the literature about global U1 symmetry breaking. That's what is broken in conventional superconductors.
Okay, thank you.
Yes, I think for the FFLO mechanism, this superconducting ferromagnet structure, so what matters is the exchange field actually.
Okay.
For the FFLO, yeah.
Okay, thank you. I also find I wrote down a question for Nicola. In your niobium diselenide data, the color plots for magnetic field along the current direction, I saw some blue region very close to zero magnetic field. And I wasn't sure how to interpret that.
Maybe I have to share the screen again. Sorry a moment, let me find the right graph because I didn't not sure I got, okay, this one, let me share my screen. Is possibly this.
Yeah, so if we take magnetic BZ equals 0.
Yes.
So and then you
so
see if see there's that blue one right there.
Oh yeah, no, that's a bit of, it's scatter. So it's the reason for this scatter, this noise in the data is that there are stochastic, that's Fourier signals, there are stochastic switching. So we had to, in principle, one should average a lot over this. We're not really sure what's the reason of that. Doesn't seem really to be related to noise. But anyway, it's a technical thing. But no, I mean, it's not significant. One should a bit defocus the view and see the
No, I appreciate the broader trends are very clear. I mean, that part is obvious. But
yeah, so
I was just curious what to think of it. But okay, so I should sort of see those patches as something like that's roughly the scale of the noise.
It's yeah, this is actually a color scale with interpolation of points, so linearly interpolates. So it's yeah, so it's kind of instead of big pixel, I make it a bit smoother, but because it's a very long measurement, as you can imagine.
Yeah.
And the longer it is, also this also contributes to the scatter, because every point are two IV characteristics, always swept from 0 to positive, from 0 to negative. You take the difference, and then you change the field, and so on. So this is.
I do appreciate that. So yeah. Okay. Thank you for the explanation.
You're welcome. Stop sharing. There is a question to the theoretician in the chat.
Yeah, I think Mars asked a question ask the general question to all the theorists. If anybody can answer this. And the question is, I heard many explanations for SDE, both generally and then in specific systems. And I am wondering how I should blend it all together. Some systems showing SDE like NVMe 790 wires versus stacks, etc., seem like they fit multiple explanations. And shouldn't some of the general explanation fit the twisted graphene too? Or does the graphene explanation not bend with Dido or Nagasa, for example? Do you have some theorists having to know the answer? Or have some opinion to this general question?
I'm not a theoretician. I could try to make a comment on this since I see no answer anyway. Is that at the moment we are trying to understand separately every system. There are several mechanisms that are proposed. We all learned that there are several symmetries that can be broken to get the diode effect. I'm just trying to speak in the most general possible way. I think we will first find the individual mechanism, and I think in a second phase we will find the common things. So that okay, this mechanism in the end is not that different from this other one, and so I think it's a too difficult question to answer now. So I see in what in our work we are. We found, first of all, it's easier to interpret what happened in junctions because in some system you can model better the Andreev bound state, which is what in the end carry the supercurrent in Josephson junctions. And in some cases they are easy to model. You start numerically, then you do analytics, and then in the plane film situation seems to be slightly more complex, but already many theories popped up. And then I think I'm sure later one will converge with a kind of unified picture of the two phenomena, because the phenomenology sometimes is similar between plane film and junction. But there are so many different mechanisms or different systems that we have explored in this workshop. I don't think one can attempt a unified explanation.
Yeah, sure. I think so. I think so. Yeah, it also seems like even very similar behavior can have different origins, completely different origins, even in like classical, or even like in some other field. So it's not a, I don't think it's a very, it's a easier to answer question.
But so my only comment is from the experiment is one should really pay attention to mechanisms that are a bit more conventional when you apply an out-of-plane field and one can have orbital effects. This is, they naturally produce a diode effect. As I showed, this is known since long time. And yeah, well, of course, it remains to be determined what creates this squid-like behavior in case, but when the field is in plane in 2D system, one knows that it's clearly a spin effect and things looks a bit more clear cut. But when is the out of plane, also in the case of niobium diselenide, because the spin is out of plane, we had to work a lot to exclude the effect of vortices. I didn't comment on that. But in other system, at least orbital effect could coexist or have a complicated interplay.
Yeah, Maz is making a comment in the chat about the role of dimensionality, since most of what we're doing has been in 2D, and wondering what can happen in 1D or 3D that would be distinct. That's, I think, a good idea and an interesting direction.
Yeah, I think in a previous satellite talk, they are doing the superconducting diode effect in a 1D nanowire system. Yeah.
Right. Yeah, indeed. There are 1D things happening.
Yeah. Sure.
But still, yeah, absolutely. So, yeah, I know it's been a long day. So if there are no further questions or topics of conversation, oh, we have one left. We have one more by Lynn. So Lynn is asking about vortex ratchet effects from the 90s and 2000s. Is that, and if those can explain any of the existing data? Is that right?
Yeah. So I've been confused because they seem like very similar phenomenon with the recent report. So, but they are found actually quite a while ago, and so I'm a little bit. I'm wondering between the difference between the mechanism causing the previous result and the ones that we are discussing right now.
Well, I completely agree with you, and this goes in line to what I was, or you thought better what I want to say, is that when you have orbital effect, there are many mechanisms that can produce this, and one should be careful. I believe that probably what was proposed in the past was exactly what was proposed, so ratchet vortices and so on. So if you have vortices, immediate mechanism that might generate the effect is that if your barrier to enter and leave the superconductor in one direction is different from the barrier for entering and leaving in the other, so this rate, then you apply a current, you're pushing vortices in one direction and another, and then you can have vortex trapping, and then you can create a dissipation with a different onset, which generates a diode effect. And this is just one example of many of mechanisms that in a way is conventional, not particularly new. Maybe one can also exploit it in a novel fashion, this thing, but it's not the mechanism that I think is discussed in this workshop. So I think it's likely that those mechanisms proposed were correct, because I think the experiment also were matching with what was observed, but yeah. Would be interesting if one can explain in the past things with the new mechanism, but it's more likely the opposite, that one can find conventional way to explain some of our experiment. So we have at least to all be careful before concluding something. In my case, was particularly important to disprove the role of vortices for niobium diselenide, because there I cannot avoid. I have to apply the field out of plane because the spins are out of plane. So, and I will have vortices anyway. I can only try to understand if they are relevant or not.
Yeah, also, I think when I'm doing the literature research, I found the ratchet effect, there's a very specific measurement. They apply the they apply the AC current, and then they measure the DC voltage of the AC current response, and they will say the this kind of specific measurement means the ratchet effect. But actually, if in this workshop, I've never seen someone did the exact same measurement. So maybe that's also a direction to see if our what we are discussing now is it similar or something different with previous ratchet effect.
Well, I can imagine, like, for our systems right now, if we do the same measurement, since we apply a AC bias in different directions, but actually the DC component is 0, but the resulting voltage is actually biased between 0 and finite value. So I can imagine a DC component, if we measure it, will be non-zero. So for me, it sounds like it's also a form of ratchet effect. I mean, I'm not quite sure how people define the ratchet effect, but I can imagine, like, if we do the same AC and DC measurement, we might probably see the same thing for superconducting diode effect here.
I think as a question of name, I think a ratchet effect is typically always associated with vortices, which can only move due to different reason, or like an isotrope in the pinning, move only in one direction. So maybe it's just a question of name. I think with that is always associated with vortices. You can call it diode, resistive diode effect, or so on.
Yeah, so I mean, with the vortex ratcheting, you know, that is very specific to the case of vortices, and there they can play even games where they're really structuring everything so that they get. I think there was even things about moving single vortices in ratchet-like fashion, right? So so that can even achieve some very interesting limit in that respect. Whereas I don't think that a lot of the phenomena, especially the theory, is sort of like bulk superconductivity kind of effect, and doesn't involve the vortices directly. So I think it would be interesting, though, to combine these things. Maybe we can see something because vortices can also be watched, right? They can be tracked, and so it would be interesting if we could
true.
have weak pinned vortices in with all this other condensed matter physics that have been revealed, and see if if really those things can be mapped onto one another in this way. That would be neat. Can a SDE be seen in a type 1 superconductor that breaks inversion? Is Maz's question. That's a great question. We should write to some people about it.
There are no type 1 superconductor in practice. I mean, when you have 3D. Okay, yes. Okay.
But then you have problems with like what does critical current mean in 3D is also has other issues. So
I just recall another question to Nicola, and since I think in one of your paper you were asked you will have a short paragraph discussing about the self-field effect in your I think the two-dagger Josephson junction. So can you explain more about, or can you share your opinion about the self-field effect in this?
I was saying that we give argument to say that the self-field effects are not relevant. So this is and this goes with the thickness. So the thinner your 2D your superconductor, and the smaller becomes the critical current, the less relevant are self-field effects. So in practice, in our case, are never relevant. It was important to prove it, but at the end, not. So there are no self-field effects in at least in the Josephson junction, which we're discussing. That's.
Thank you.
And we can also imagine playing games with, pinning the superconductors, pinning the vortices strongly versus keeping them weak, and seeing how these things play out in those different kinds of contexts.
Well, this one thing was that shown by Dennis yesterday. So with inductance measurement, you can see how the vortex shake around the pinning center.
Yeah.
And if you imagine that the pinning center is a delta function, you are just watching the core of the vortex in a way.
Yeah.
And so if you have rush bar, you have as a result that the vortices get squeezed and stretched. This produces more pinning and anisotropy. Would be interesting. So we have also seen how the depinning works in this case. Maybe it would be interesting with to see also the effect of the ratchet. In this case, there is a big field, many things to study. Although for us, it really would be also nice to study the very condensate without vortices, but it's exactly difficult because of that. You really need to compensate very carefully the out of plane field, because the kinetic inductance in our field is say 40 nanohenry, and the vortex is 40 microhenry, so it's a factor 1,000 in between. So one needs really to have the smallest possible out of plane field.
Yeah, I think Mark's comment again said, what about NV diamond center and looking at a superconducting diode, trying to look at the vortices and see if they are retching.
People have various techniques for looking at the vortices, right? They've got the scanning squids and other kinds of microscopy. So
I think I also see a paper about direct observation of vortices in Josephson junctions. They use STM to measure to characterize the vortex in the Josephson junctions and as well as in the superconductor.
Or were they Abrikosov vortex or Josephson vortex?
Josephson vortex.
Yeah.
Okay. See.
Yeah, that's fun.
Yeah. Yeah, Mark's commented, let's look at superconducting diodes that way. Yeah, it's a fun direction.
Sure. Yeah. I mean, and also for systems in which we don't understand where the time reversal symmetry breaking is coming from, right? You may want to have a magnetic imaging system, a local magnetic imaging system. So Hung, that might be relevant for you to think about for your device.
Yeah, true.
All right. It looks like we're winding down a little bit.
Yeah.
Thanks everyone for coming. I think it's been a really successful workshop. I've learned a lot, and we'll work on getting the recordings posted as soon as we can, and we will alert everyone once that's ready to go. So thanks again to all the speakers and for all the participants, and hopefully, we'll keep having developments in the field over the next few years and have a recap, not a recap, a new updated workshop at that time. So see you all.
Thanks to the organizers.